Welcome back. This is lesson 3. You should watch lessons 1 and 2 before this, otherwise it's not going to make a great deal of sense. This is for the AQA Astrophysics section of the A level. I'm going to be looking at angular resolution. I'm going to actually go to this part of specification before I do this part, because you really can't do this without working out what resolving power is first. So specification people from AQA, you might want to put these in a different order. But anyway, so this part I'm going to do first, just this first 2 sections here. I'm going to be able to explain the Rayleigh criterion, and then to evaluate a telescope using its resolving power. I'm going to leave collecting power for the minute, just because that takes in a different set. So I'm just going to do this one section. I'll leave it a short video, but this is quite intense. So I'm just going to do this one on its own. Then I'm going to go back to the collecting power. You'll see why, because a lot going on. Resolving power. It's not power. It's not a power. It's not watts. It's not anything like that. It is actually an angle, and it's an angle in radians. It's actually, the better term is angular resolution. In other words, how small can you observe things? And when I say small, I don't mean the size. I mean the angle at which you can observe it. The X sub 10s on the sky. So you've got your angle, how much this angle is between my hands. Now, what you actually look at when you look in the sky is that if you take a lovely picture of the telescope, you don't actually see little dots. You actually see little tiny diffraction patterns. And if you zoom in onto any particular point, you actually see something that looks a lot like this. And this is a single slit diffraction pattern. If you slice it in half, it looks a bit like this. If you have 2 objects, and if you zoomed in on them on your image, you'd see these sort of concentric circles around them. These are 2 single slit diffraction patterns, and it's a single slit mainly because it's a single hole. The telescope is actually acting like an aperture on the sky, and you're allowing light to come in through that, and you can imagine all the light is flooding by, and the telescope is actually only catching a very small amount of that light. Now if those objects get nearer and nearer, they start to become look like a single object. Now what Lord Rayleigh did was worked out that what is the minimum separation that those objects can have, given the wavelength of light and the size of the telescope. And that's what they depend on. The angle, the minimum angle which we can observe, is dependent on the wavelength of the light that we're looking at and the diameter of your telescope. Of course, wavelengths, we can look at the things in the sky with all sorts of wavelengths. All the way from gamma ray all the way to radio waves. And that's the whole point of astrophysics. We use all those types of telescopes, from gamma ray telescopes to radio wave telescopes, and everything in between as well. I spent my career doing microwave astronomy. People think, what? Microwave astronomy? Really? Yes, microwave astronomy. A lot of microwaves come from space. Cosmic microwave background, for instance. So, and then when we looked at the Hubble, the ground-based images, you see this ground-based image here is a bit fuzzy. But then look at the Hubble Space Telescope. Much higher angular resolution, a larger resolving power, even though it's not a power. It's an angular resolution measured in radians. In other words, this image can discern things that have a much smaller angle on the sky compared to this image over here. Okay, right, so how do we do it? How do you need to nail this? There's your equation. So in your notes, you have to write that equation. So I would put it under the term angular resolution. Resolving power is very misleading, but you do need to be aware of it. Theta, which is the angle, the smallest angle, is lambda divided by d, and d is the diameter of the telescope aperture. Now, this is Lord Rayleigh here, real name John Strutt, and this is what he said. 2 objects will be just resolved if the center of the diffraction pattern of one image coincides with the first minimum of the other. And you can see why. On the previous image, I had those 2 parts. You can rewind and go back and have a look. The peak of one coincides with the first minimum of the other, and that's as near as they get. That's as near as they get. So get your calculator out. We're going to have a estimate these angular resolutions of these. So a small refractor with light. So a small refractor, let's say that's about that. So estimate that size in meters. So a small refractor will be about that. Estimate that size in meters. So that's about 15 centimeters. That's the end of your telescope. Convert that to meters, which is going to be the diameter of the end of your telescope. And then roughly estimate what your wavelength of light would be. in nanometers, and then of course convert that into meters. You end up with a ratio with no units, radians. Even though we call it radians, it's actually a ratio that has no dimensions. Even though we pop radians on the end just to make sure we know what we're talking about. And then the JCMT, 15 meters, 15 micrometers. Go and look at what micron is if you want to, what the power is, which you do that. And then, of course, your wavelength divided by your meters. Notice I'm giving it in the wrong order. This is what examiners do as well. They'll give you it in the wrong order. You've got to work out that it's the wavelength divided by the diameter. And then you start getting numbers in the 10 to the power of minus something. That's normal. Some of the best telescopes in the world have 10 to the minus 8 radians as their angular resolution. Your eye is about 10 to the minus 3, and telescopes are all the way in between. Some radio telescopes that are in something called an array that do interferometry, which is a very clever way of being able to make telescopes seem like they're bigger, can get down to very, 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 very low angular resolutions, which is a good thing. Low angular resolution is a good thing. Okay, so here we are. These are these ones here. Now, I mentioned about collecting power. It's just proportional to d squared. Now, the only way the examiners of telescopes at Hubble, you would then, there we go. Right, no, you can't see it. Never mind. Try again. Okay, a little bit. So what we've done so far. You can do some revision. I've put some gravitational revision on here if you're going to watch some of the other videos that I put on, but I'll concentrate on just the Astro one here. Cassegrain telescope, you need to be able to draw a Cassegrain telescope. Chromatic aberration, you need to be able to say what that is. Multiple focal points cause indistinct images. Reflection spherical aberration, so that's when you've got a reflected telescope, where how does that cause indistinct images? Compare reflection and refraction. Be able to use the Rayleigh criterion using wavelength and diameter of a telescope to get the angular resolution. I've got F here, that's not Facebook, that is focal length of the telescope. Angular size, height, distance away. Refraction telescope is those two lenses, lots of rays on it, practice that, and just hiding behind me here is angular magnification. Angular magnification can be the ratio of your objective to your eyepiece lens, but it can also be the ratio of your angles of one of your unaided eye compared to your A. Kepler proof, you're going to have to do the proof of the Kepler's law in a bit, but leave that for now. Okay, practice. Supermassive black hole, center of galaxy, difficult to resolve images in this region around the black hole directly. Sketch on the axis the variation of intensity of the diffraction pattern produced when a light from a point source passes through a circular aperture. So all that is just an image. Let's try and get this on here. This is what I was trying to do before. Is it going to work? Okay, so you're, oh lovely, there it goes, like that. Pen goes remarkably quickly, I must say. You should try and use this. Oh, and that should look roughly the same size as the one outside. So you can try that. You can probably a bit tighter if you like, but generally that's the right shape. And then, of course, the Rayleigh criterion is used to determine the smallest angular separation between 2-point objects when resolved by a telescope. Perfect definition. With reference to diffraction patterns, Rayleigh criterion. So you've got to be able to mention the fact that you've got these overlapping patterns. One pattern is exactly, the maximum of one coincides with the minimum of the other, and the angle, of course, is the difference between those two peaks, between those two objects. Only 2 marks for that, pretty stingy. Okay, so we've just covered the minimum resolution of the telescope, the Rayleigh criterion. I just popped in the diameter there as well. Radians as an angle of unit. I haven't done CCDs yet, I haven't done this, and I haven't done these top bits because that's going to be lesson 4. Okay, go back, look at the whole thing, do the notes, make sure you know the Rayleigh criterion inside and out. I'm going to be telling you how you can evaluate a telescope in comparison to things that you see in the next lesson and the lesson after that. Okay, bye now.